my name is Erin Rebello, and I'm making this video to show you what I've been up to for the past few months. Way back at the start of summer, I got involved with the Institute for Student Science and Technology, and I basically got to do a research co-op where I worked with Dr. Brad Bass at the University of Toronto. From there, I worked with 4 other girls, and we all had our independent research projects, but we're still collaborating because we were using the same software. This software, which you can actually see right before you, is known as COBWEB, which stands for Complex Organized Behavior Within Environmental Bounds. It's an agent-based modeling software, and it can be used for a variety of purposes. In the past, it's been used to model ecosystems, brain disorders, and much, much more. I decided to use COBWEB to model bacteriophages and how they can be used to treat antibiotic-resistant illnesses. Antibiotic resistance is a huge issue, especially because we've been overusing antibiotics, and we now are finding that bacteria are having a greater resistance, and it's harder to kill them with modern antibiotics. For that reason, we're turning to other solutions, such as bacteriophage therapy. A bacteriophage essentially is a virus which is able to get into a cell, multiply and make copies of itself, then lyse the cell, burst out, and continue the cycle all over again. And I know what you're thinking. Why would you introduce a virus when you already have an antibiotic-resistant bacteria? Well, it's actually quite simple, because bacteriophage therapy is safe, effective, and it's very precise, meaning that you can target a specific cell, in this case, the bacterial cell, without harming your other healthy cells. And that's exactly what I'm modeling here today. The yellow cells you see, the yellow little triangles, are healthy cells, whereas the blue cells are bacterial cells. And currently there are much more healthy cells than bacterial cells. Also, these little yellow and blue squares are different particles representing nutrients and food available to the cells in the host. So when I play this, and I'm going to play it up to 550 ticks, you're going to see some changes, and you're going to see how the blue cells really start to take over. And it starts off kind of slow, but you'll see that over time, the number of yellow cells decreases because the blue cells, which are very competitive, start to take over the resources. And right now, it's already visible. And now we're at the point where it seems like the blue cells have almost outnumbered the yellow cells, which is a really bad situation. So what are we going to do? We are going to insert an agent. We are going to insert an agent type 4, which are the bacteriophages. These little red triangles represent the bacteriophages, and we're going to input 3 lines worth of bacteriophages. And this is just to show how you would insert bacteriophages during an illness to kill off the bad bacteria, so in this case, the blue cells. And it's really cool because although you'd expect this to perhaps kill all the other cells, it only targets the blue. So you'll see the results in the end. Just wait. And now we're going to start up till tick 1000 and restart. And you can see how the red cells the bacteriophages only prey upon the blue cells. And there's barely any blue cells left. I can see like maybe 1 or 2. And they're just about gone. And another cool thing is once the blue cells are gone, because there's nothing for the red cells to feed on, you'll see that the red cells will also disappear, and you'll be left with only healthy yellow cells. So we're going to run it for a few more ticks. And as you can see, we're already clear. We didn't even get to 1,500. But I'm going to stop it here. We're already clear. No red cells, no blue cells, only healthy yellow cells. And what I did is I took the data from this simulation, and I actually extracted it into an Excel spreadsheet. And I know it looks like a lot right now, it's just a lot of data thrown at you, but I whittled it down into the important categories. And as you can see, there's a chart created right here which shows the correlation between healthy cells, antibiotic-resistant bacteria in blue, and bacteriophages in red. So as you can see, as the antibiotic-resistant bacteria takes over, you get a decline in your healthy cells. But as soon as the bacteriophages take over, snap, like that, you see a complete reversal and you get your healthy cells in the end. And this was something that I thought was really cool. I think it's definitely super applicable to the modern world. And since that experience over the summer, I was actually invited to stick with URX, which is the permanent COBWEB program at the University of Toronto, and it's like youth-led, and it combines both high school students and undergrad students, so I'm super happy to be a part of it. And I've also worked on new projects. So a project I'm currently working on is modeling the Permian-Triassic extinction and how some species went extinct while others were resilient and were able to survive. So that's another really cool thing. And I don't know, I just thought this was super interesting because it connected my love for biology and turned it into a love for working with data and working with computer programs. So I thought that was super cool. Thanks for watching.